All right. Hello, everyone. Thank you for tuning in to today's installment of the Corundum Developer Meeting. So let's go ahead and get this show on the road for the August installment. Um, all right. So agenda announcements, status updates, same as usual. Announcements. The next developer meeting is going to be September 3rd, and I'm going to be going to DC for the next month and a half. So this one will be live from somewhere in DC. I don't know exactly where, but we'll figure it out. Um, yeah, the next Switch meeting, I think that's going to be TBD. Carlos, you might have given me a date, but I'll just leave it TBD for now. Carlos is working on his, PhD dissertation, both the paper and the presentation and whatnot. So, he's got a lot of work to do on that, and it's not going to be doing a lot of stuff in the lab, that results in status update meeting type stuff. So we'll circle back to that at some point. And also we might be getting a practice talk at some point. We'll see. So more details on that later if people are interested in that. Stay tuned. Um, yeah, only a couple more meetings. I can't believe it's August already. Um, time flies, right? All right. But moving on to the status. All right. So I've been working on the rewrite piece by piece. I figure I might as well have a little section on updates to the taxi library, new modules, stuff that's been ported, things like that. Just to keep all that self-contained. Um, oh, I guess I forgot to update. I moved some stuff around. I forgot to update this slide. All right. So I haven't done much more with the new Mac and Fi wrapper module, but I have been doing a little bit more with the time sync test measurements. Um, Let me just say that I can't remember exactly what I reported the last time around, but the performance is not quite as good as I thought it was. There's another little characteristic of the receivers that has popped up that I'll go into a little bit more detail about later in the presentation. I'm also going to talk about the plans for the next generation version of Corundum and also the current progress on the Zircon IP stack, which I just did kind of a first light test on yesterday of well, not exactly echoing packets back, but turning around payloads, which worked more or less as expected. Obviously, there's still some bugs in it. It's still kind of mocked out in a number of places, but it's starting to show some signs of life. So that's a good thing. All right, moving on to the details here. So the one of the main things that I'm working on is kind of a long-term thing is to rewrite Corundum and all of the associated libraries in System Verilog, um, and move a lot of this into the new taxi transport library that I have up on GitHub. And the idea here is that you can continue to use it for open source projects and research and stuff under the CERN OHL strongly reciprocal license. But for commercial stuff, if you don't want to release source code for your entire design, then there will be commercial licensing and support available for everything in the taxi transport library. So I've been chipping away here and there at transferring over and porting the core library components. That's a little bit more details on that in a couple slides. I also have a bunch of new stuff that's being added to the taxi transport library piece by piece, and lots of updates and refinements, and example designs as well that are tailored to some of the separate subsystems. All right, so for the porting progress, there were a number of straggler modules for AXI Stream. I don't think I've finished quite all of them, but I think most of it is in there right now. There's still a bunch of stuff that I need to do on AXI and AXI Lite, and all the PCI Express stuff needs to be squared away as well. I'm also working on the new Zircon IP stack to replace the old UDP IP stack in the Verilog Ethernet repository. Hopefully that stack will be available for use in the next couple of months here, but we'll see about that. More details on that later. I'm also putting together updated example designs, and I think last time around the main to-do item on this was or one of the main to-do items was the I2C init code, so I can bring up boards that require things like PLL chips for the Ethernet interfaces and stuff to work. So I've since gotten that squared away, and I've re-added the HTG 9200 example design, so that works. I haven't done anything with the FMC adapters. I know I had a couple designs for the 6 gang QSFP 28 adapter, and I also have a 10x SFP plus adapter that I can add support for as well for a couple of boards, potentially. Those are still to-do items at this point. But yeah, so that's coming together. And all the example designs that have a serial port also have XFCP for, monitoring and statistics and things like that. Although the big to-do item there is getting the Python code organized and integrated into the repository. I haven't had time to sit down and kind of figure out how that needs to work. But I'll get that squared away hopefully soon. Okay, so moving on to the taxi library updates. So over the past, I guess, since the last developer meeting, I've ported a couple of additional modules. I got the demultiplexer and the switch modules ported over and updated and integrated into the taxi library. I also moved over a few I2C modules as well, the slave and the AXI Lite master module, as well as the I2C init code as well. So that's all operational. Then there's a couple of additional modules I've been working on. I've got a concatenator module, which takes basically it has a configurable number of inputs, and then it will take one packet from each input, connect them end to end, and spit out the result. So you can use that for like attaching headers onto packets and things like that. And then I also have a slicer module that I'm working on that does sort of the opposite, right? You give it an EXI stream packet along with an offset and a length, and it will extract the corresponding portion of the packet. More details on that in a minute. I've also added, again, a couple of example designs to the HTG 9200. That's in the repository. I'm working on the ZRF8EM example design for a high-tech global RFSoC board that we picked up recently for the research project. I may also be adding one or two other variants of that same board. We'll see. But at this point, the plan is to add the EM variant because that's the board that I have at the moment. All right, so going on to the little bit more details on these new modules, the AXI Stream Concatenator, it has multiple inputs, and you can configure, with a parameter how many you want, 2, 3, 4, whatever. What it does is it accepts packets from each input in sequence. So if you have 3 inputs, it'll accept from the first input, then the second, and then the third. And then the packets will be barrel shifted as necessary and concatenated end to end. So this works even with a data width, of more than 1 byte. And yeah, if you have 3 inputs, it'll take 3 packets to produce 1 output, 1 from each input. I can't think of a better way to configure that right now. There might be some other options, maybe configured via T-user or something if you just want a couple of pieces or skip a channel or something, but the core functionality at this point works. But I potentially need some better handling of some of the sideband signals, particular T-user, and maybe some adjustments to improve the throughput. Because right now I think there's a potentially a bit of a stall when switching from one input to another, which reduces the throughput on the output. But this does work for effectively any. I don't know about any data path width, but widths beyond one byte. So if you do like a 32-bit 4-byte interface, it works and it'll shift things accordingly, even if the packets other than the final one are not multiple 4 bytes in length. The other module I've been working on is the AXI Stream Slicer. And the idea with this is you can specify a length and an offset via this AXI Stream command interface, and then it will accept a packet on the main input interface, and it'll truncate and shift the data in that packet accordingly. So you can use this to, for example, extract payloads from network packets to strip off headers and padding, things of that nature. Unfortunately, right now it only works for a single byte wide interface. I need to do some additional work to get it to reshuffle things appropriately when you're using wider interfaces. And I also probably need to make some additional adjustments for handling sideband signals properly, right? Like if you cut off the end of the packet, but it turns out T user was set indicating it's bad frame, what we should do is hold the last cycle and then transfer it out. So I'll circle back around to that after getting the core reshuffling part working properly. So this one's I think not in the repo yet. The previous one, the concatenator, is. So you can take a look at it if that functionality is useful for your projects. All right, so then I have the Mac Phi and DT wrapper. I guess there's nothing really new on this since the last update, aside from the fact that, the news on this is that I've added support for 32-bit, both normal and low latency, um, both for the separate Mac and Phi and the combined Mac and Phi. And I've tested that on, I guess, a couple different boards at this point, and so far, the low latency stuff seems to work as expected. There's still a number of to-do items in terms of supporting the lower speed stuff, making wrappers for Intel parts. I need to do some reworking of the timestamping subsystem, including making corrections for the gearboxes and such. But one step at a time. It's the core functionality at this point is there. Let's see. I got a few more details on the low latency mode. Nothing really new here. I think I've talked about it this last couple of meetings, but the idea is that you can switch between normal latency and low latency mode with a single top level parameter. In general, it makes sense to use the normal mode unless you really need the low latency, because the low latency one runs at a slightly higher clock frequency and it consumes a little bit more in terms of logic resources. So if you don't need the time sync performance that it will eventually provide, and you don't need the shaving off a handful of nanoseconds of latency, then you can use then you should probably be using the regular non-low latency mode. But it's a very easy trade-off to make. You can just flip the one setting, so you can always flip back and forth if you're having timing closure problems or whatever on a case-by-case basis. All right, so I also added the 32-bit Mac and PCS. So now that I have the synchronous gearbox support working at 64 bits, it wasn't all that much additional work to make this work at 32 bits. And the big thing here is that it cuts down the data path width by a factor of 2. So 1, it's lower latency. 2, it's smaller footprint. I highly recommend, if you're running at 10G, to use the 32-bit Mac and PCS if you have a fast enough part to close timing at 300 megahertz instead of 156. I guess I've tested it on a couple different parts at this point. But yeah, the latency should be, I think it did some back of the envelope calculations. It should be shaving off, maybe 40 nanoseconds or something, maybe less than that, versus the normal latency version that uses the asynchronous gearboxes. Oh no, I guess right. It should be shaving a number of nanoseconds off versus the 64-bit version as well, because it's running at a higher clock frequency. So that's probably something that that somebody could characterize. That would be interesting to take a look at, right? You get the 64-bit version, the 32-bit version, the low latency, the normal latency. What are the latency measurements for those, and the resource consumption? Some point, maybe I'll have time to sit down and actually do a proper job measuring that. I think maybe once I get the better timestamping support implemented, then I can get really good latency numbers. I do have a couple of numbers here for the 32-bit Mac and PCS, comparing the 64-bit versus the 32-bit. I think these are both the low latency variant. And basically, it's a 50% LUT savings and a 25% flip-flop savings over the 64-bit version. So that's a pretty significant reduction in the overall footprint. Obviously, the trade-off is that you're running at 322 megahertz instead of 161 or 156. So definitely a useful optimization option to have. All right, so the other thing that I've been working on here is the 25G Syncy demo on the Alveo U200. I guess I talked about this the last time. I did a very rough demo where I glued the new 25 gig max onto Corundum and did some relatively rudimentary testing. I also did some testing through a longer length of fiber, using the LR4 optics instead of CWDM4, and then through, I guess, about 3 kilometers of fiber instead of just a couple of meters of fiber. The PLL locks, but the output has a fair bit of noise in it. I'm not sure exactly where that's coming from. If this is a problem with how I'm doing, there's several different potential sources of that, right? So one of them could be that software PLL is not really tracking properly. Another possibility is that the DDMTD is producing more noise than it should. Another possibility is that this is just the RX CDR, for example, tracking and producing a lot of, jitter internally that shows up through the DDMTD as noise. So not sure, I need to do some more work to try and pin down what's going on there. But a more worrying thing that I discovered is that there seems to be some temperature-related steps of several picoseconds in the DDMTD output. I suspect this is coming from the buffer bypass logic. So got a couple of plots here that we'll take a quick look at. So this was the old demo at 10 gig. And when you run it with the, well, go back for a second, it's got the two Alveo U200s that are cross-connected with CWDM4 modules, and that's going through this optical delay line. So the idea is that one of these things acts as a master. It free runs its internal oscillator. The second card synchronizes to the master, and it basically sends its synchronized clock back through the link. And then on the master end, we can compare those two and get a relative measurement of the link delay. And then I have a little script that cycles the position of this delay line. And then we can look at the output of the phase detector or of the DDMTD logic and figure out, what things are looking like. So this is the result of that. And as you can see, we can measure offsets of the delay line that are, a handful of picoseconds, right? So the 10 picoseconds is, very easy to see. Even getting down to like 2 or 3 picoseconds, it should be possible to pick that out. So what I did is I updated that for 25G. Now with this one, I was also running through much longer length of fiber, and as the temperature changes, the delay through the fiber changes, so we get a bit of a slope here, but we can still pick out these 10 picosecond steps, although as you can see in the middle, it's kind of hard to discern those steps in all of this noise. But the bigger issue that I discovered is that there seems to be these steps that occur under certain circumstances in the output of the DDMTD data, and I ended up effectively removing all of the optics. So this is tested with an electrical loopback. So there's, no optical transceivers, no fiber, no nothing. It's just the FPGA connected back to itself. And we're still seeing these spikes of, they're around 15 picoseconds or so. As far as I can tell, they seem to be related to temperature. So, as the room warms or cools, obviously this is going to cause the FPGA die temperature to change. At certain temperatures, it seems to be like moving from one delay to another. And in doing so, you'll see some of these spikes for some period of time. So what I suspect is going on is that this is coming from the delay line tap switching in the buffer bypass logic in the GTs. So not sure how much I've discussed this previously, but the inside of the GTs, the clock used on the FPGA logic side is provided by the FPGA fabric logic. It's not provided by the transceiver. So the way the clock works is the transceiver has an output that drives the global clock network. Then it comes back and drives the TX RX user clock inputs on the transceiver. And this means that the internal transceiver X clock is not aligned with the TX-RX user clock that's, coming in from the fabric. So the delay alignment logic, what they do is they add a delay line, I think, on that output that feeds the fabric. And it will adjust that delay line with logic internal to the transceiver to try to bring those two clocks into alignment. And when they are close enough, then you don't need, an async FIFO or buffer inside of the transceiver in order to make it work. But the problem is that if they're using a delay line, then it's going to have some tap size. And as the temperature of the FPGA die changes, then the delay through the clock network is going to change. And eventually it's going to be switching from one tap to another. So I suspect that's what we're seeing here. As the temperature changes, it's moving from one tap to the next. And it does so without any kind of any kind of dithering. So you'll just be at one tap value, and then bink, it'll jump to another tap value, and then you get this big 15 picosecond step. So I need to do some investigation here to try and figure out exactly where this is coming from. Is this actually the buffer bypass logic, or is this something else? And then also to see if maybe there's some way to improve that. There was a presentation at the FPGA Developer Forum, I guess earlier this year at CERN, where they were talking about doing, what was it? I think frame clock recovery using the transceivers in Xilinx FPGAs. And they did a pretty deep dive into how you can screw with some of the internal components in the transceivers, including some of the buffer bypass logic, in order to get this frame clock recovered as precisely as possible. And they included some bits in some of the configuration registers. So stuff that's not documented in the Xilinx user guide. So I don't know where they got this information, but it's I think it's worth doing some experiments to see if to see what happens if we poke some of those bits and see if there's, maybe a way to, I don't know if it would be possible to, manually drive these delay lines and maybe introduce some dithering or something else. I'm not sure. But it would be nice if there's some way to improve the situation so we don't have these big steps. So yeah, it's possible to dither. That might work pretty well because then you get kind of a nice smooth transition. But with something like that, I think the hard part is not so much the controlling of the delay line, but it's figuring out how you're actually going to do the feedback, because the measurement has to be done inside the actual transceiver to figure out whether, one clock or the other is ahead or behind. So I'm not sure if it's possible to get access to that somehow. So more work to be done here, but the I guess middling over 15 picosecond steps is progress. Not sure. Hopefully more details to follow on that. Previously, I also presented a couple more notes on timing and clocking for these things. So for my original idea for doing this high precision timing stuff is at 10 gig. Well, you can run the transceivers at different modes. So at 10 gig, if you run it at the 32-bit mode with the async or with the synchronous gearbox, it runs at 322 megahertz. If you run 10 gig at 64 bits, it runs at half of that. 64 bits with 25 gig runs at 400 and change megahertz. And then the CMAX run them at 80-bit. So at 25 gig, that's at 322. For building the White Rabbit switch, they kind of want to run everything at the same ref clock, or it's not so much the same ref clock, but they want the internal frequency to match the external applied reference clock, so they can actually measure the phase delay between the two. So having 322, 161, 402, and potentially like 125 or 62 and a half for 1 gig, you don't have enough reference clock input pins on the transceivers for that. So it's like, well, okay, would it be possible to get, both 10 gig and 25 gig running at the same frequency somehow? But I realized, well, hey, hang on a second. This 25 gig at 322, that's the same frequency as 32-bit 10 gig at 322. So if we do some wacky custom async gearboxes to get from either 32 or 80 bits to 66 bits, then maybe we can do when we're in 10 gig mode, then we can run at 32 bits at 322, and then at 25 gig mode we can run at 80 bits at 322, and now these frequencies will all match with the external reference clock. So we'll see about that. It seems like it could be a promising approach, but this is going to require some additional fabric logic to make it work. So potentially a longer term thing to sort out, but interesting nonetheless. All right. So this is something I talked a little bit about for the next generation version of Corundum, the idea that I have is to, well, obviously take Corundum and rebuild it in System Verilog, just like the rest of the taxi library. But in doing so, it might make sense to build a couple of different variations that have different optimization points. So I've had a couple of people ask about, hey, could you run Corundum at like 1 gigabit per second, or could you put it on, a small SoC or something like that? Well, the default version of Corundum, no, because it's massive and all of the control path stuff doesn't really scale with the data path. So that's the idea with these variants, is that, well, we can build a control path with a different set of optimization parameters for different use cases. So for Corundum Micro, this is intended for like SoCs where you have a handful of ports at 1 gig, maybe up to a single port at 10 gig, but probably more like a handful of ports at 1 gig. The next step up would be Corundum Lite, which is more or less equivalent to the current version of Corundum that supports a handful of ports at 10 gig, 25 gig, maybe up to one, possibly two ports at 100 gig. And then the idea is to have a much more high performance Corundum NG version, which would support very high packet rates and lots of ports. And the idea is to be able to use the same driver and have a very similar software hardware interface for all these designs, right? The same kind of descriptor queues for packet transmission, and some kind of queues for control, things of that nature, just to keep things as consistent as possible. And then the plan is that all of these basic designs will support, or all the designs will support the basic offloading and timestamping. So checksumming, segmentation, and timestamping. So a little bit more detail on each of these. Corundum Micro, the idea is that it's going to be a size optimized design that will use lots of cycles to do things. Because at 1 gigabit per second, you've got, potentially 64 cycles per packet minimum to do stuff. So that means you can, I don't know about toss a soft core at it necessarily, but you can have some, kind of a micro-coded sort of design where you can have lists of, and sort of like a custom CPU, but very stripped down and very specialized sort of thing, with the potential for, providing a very small footprint. This is really intended for like SoC devices with an AXI interface, but it would also make sense to support PCIe, mainly for development reasons. But maybe somebody wants a really small footprint, 1 gig NIC, and that doesn't need to go with an SoC, but needs to be installed in a server or something. So it would make sense to support PCIe. So I got to think about exactly how that would look from a, what the interface would be on the actual modules, but that I think should be relatively straightforward to do. The idea is also to support the basic NIC offloads like checksum and segmentation stuff, scatter gather DMA, and timestamping. Checksumming, I think at this point is a little bit of a, I'm not 100% sure how to handle that, because if we're optimizing it for really small size, we don't want to necessarily put a really big packet buffer in there. And checksumming, you have to read the entire packet content so you can compute the checksum and stuff it in the header. So I got to think about that. There's a couple of potential approaches for that. One of them is that maybe you just need that big buffer if you want to do checksumming. Another potential approach is to read the packet twice, read the packet once, checksum it, then read it again and insert the checksum and send it. That might be a reasonable option for these lower rates, but it's also not super efficient. So haven't really gotten my head fully wrapped around that, but that's kind of the idea here. This is going to be kind of a self-contained core that you'll be able to drop down in a block diagram or whatever, which is quite important when you're doing like Zinc stuff, because everybody uses block diagrams for that. And this also might be a nice method for prototyping the new descriptor format and developing the driver, because it's a lot easier if you have kind of a micro-coded design to make modifications to it, especially if it doesn't need to run very fast, versus if you're trying to do all of this, but also support, operation at 100 gigabits per second, where you got to process, 1 packet per clock cycle or something. So that's the idea with Corundum Micro. Corundum Lite, the idea is it'll be similar to the existing design, somewhere in the middle of the performance space. kind of the aggregate bandwidth of around 100 gigabits per second. So a handful of 10 gig, 25 gig ports, something like that. This one will add support for, multiple TX-RX queues, SRIOV, that sort of thing. And ideally, this will also support, mixing PCI Express and AXI on the host interface. So um, the idea is that if you put this on an MPSoC type board, then you could have PCI Express to the host and AXI to the SoC. They'll probably support an application section, although it's probably going to be optional, so you can turn it off if you just want the core NIC functionality. And I might also make this more self-contained. We'll see. And then Corundum NG would be the highest performance level. So this one, most likely, I'd be targeting natively the Agilex IR tile. And we'll see what we can do in terms of the timing performance, in terms of the throughput, because yeah, making anything run at 500 megahertz on an FPGA is tricky, and you got to run close to that in order to get the PCIe Gen 5 by 8 or by 16 link fully saturated. I'm also going to be potentially looking into multi-headed PCIe for Corundum NG, because while the Intel parts support Gen 5 by 16, Xilinx parts only support Gen 5 by 8. So if you get like a one of the newer Versal parts with the CPM5, if you wanted to run at the full bandwidth, you'd need to dual bifurcated Gen 5 by 8. So the ability to glue that back together would be potentially useful there. And also potentially to support things like local AXI DMA into the DRAM and HBM, and definitely providing an application section. That would be a very important piece for doing any kind of offloading into hardware. All right, so that rounds out the Corundum stuff. Hasn't been much movement on that because I've been spending my time working on the timesync stuff and the new network stack Zircon. So let's take a look at that. So Zircon, the idea is to build a replacement for the old UDP IP stack that I had in the Verilog Ethernet repository. So the plan is to support IP and UDP natively and have a mechanism for supporting additional protocols like TCP and RDMA. It's going to have more of a socket style interface where you can send it commands to like open a socket or start listening on a port, that sort of thing. And then ARP and whatnot will be handled either by a soft core or by some sort of more compact state machine running inside of the stack. Embedded RDMA is potentially on the roadmap. We'll have to see about that. And one of the main things that I want to be able to do with Zircon is to use it in Corundum for supporting some of these higher level protocols. So RDMA and TCP, that could definitely be useful, but I think the big thing is like SRIOV support, where Zircon can provide the multiplexing in hardware of the data coming into the NIC. Because otherwise, this is a kind of a problem, right? It's one thing with SRIOV to implement multiple PFs and VFs, but if you can't go figure out which PF or VF to send an incoming packet to, then that kind of defeats the purpose. So Zircon is hopefully going to provide a mechanism for doing that. All right, so how is this going to work in reality here? What I'm thinking about doing with the stack is to provide multiple streaming interfaces that can be connected to internal clients. So if you want to have several different hardware blocks that are doing different things, they can each have their own streaming interface. And this reduces head-of-line blocking. So if you have to wait for an ARP lookup or something, then the other clients will still be able to send and receive traffic. Versus the old stack, there's just a single streaming interface, and if you send something that needs an ARP lookup, then the whole thing gets blocked until the ARP lookup completes, which is decidedly not so great. And then what I'm planning on doing is providing 4 streaming interfaces for each client. One set is the data TX and RX, and then another set is the control TX and RX. And this gives you a relatively simple mechanism for communicating with the stack, where you can basically just send commands over these ports instead of like figuring out a register map and we got to write this register or that register, and things can move around between different versions of the core, different configurations of the core. These control interfaces are going to be, standard format. You have like an opcode and, the associated, parameter data. You push that into the streaming interface, and then the stack will take care of it from there. And this is how you make requests to open connections, or how you get notifications of new connections, that sort of thing. The data interfaces will then carry the packet data with the headers cut at a configurable point. So you could get the whole packet, you could get just the Ethernet payload, just the IP payload, just the UDP payload, depending on how you configure the stack. And you could potentially have multiple different flows multiplexed over the same client interface. So it's not configured. This is not going to be configured on a per client interface level. It's going to be configured more on a per connection level. So on one client, you could be getting both Ethernet traffic where you're getting the whole packet, as well as UDP traffic where you're getting just the payload, for example. All right, so let's just go through just a real high-level example of how this would work for, say, UDP. If you wanted to send a UDP packet to another host, there's a couple of steps. The first is that you would issue a request to the control streaming interface for that client to open a connection. You'd specify the destination address on the port that you want to connect to. The stack then assigns a source port, and it returns some context information. And I haven't figured out exactly what the format of all these are going to be, so I'm not exactly sure what information is going to be contained there. But the most important thing is that it's going to give you a tdest value to use when you want to send data to that host. And then all you do is you send the AXI stream data. You send the payload via AXI stream with that tdest value, and the stack will look at that tdest value and go, okay, well, this is going to go to this particular host. It will generate the headers and send it out the door. And at some point, it has to perform likely an ARP request. So if it doesn't have the address yet, when you try to send the packet, then it'll block on that UI on that UI port. If it does have the address, then it will go ahead and accept the packet and send it. And there's also going to be a way to basically get a notification of when that connection is ready, when that ARP request has completed. So I think there's going to be not only a notification that you get basically in response to the initial request to open the connection, but subsequently you'll also get another notification saying, hey, the ARP request has completed. Here's the hardware address, and this link is now ready for, or this connection is now ready for use. So that's kind of the way I envision that working. And the great thing about using the streaming interfaces is that it doesn't take a very complicated state machine to issue these requests. All right, so that's the UDP client. Now, what about a server? Server process is very similar, but instead of issuing a request including the destination address, you give a request to the stack to open a connection with a particular listening port. The stack then returns context information, including a TID value, which the stack will use to indicate when you have a connection for this, when you have an incoming connection for this particular context. And then when a packet comes in for a remote host, you'll then get a notification that includes the IP and port, and that sort of thing, as well as a tdest value that identifies that connection. So when you want to respond, you'll just send the response data with that tdest value, and the stack will do what it needs to do to transfer that, to build the headers and send the packet back to the host that made the request in the first place. So relatively simple thing to do. You don't need to be dealing with addresses on the at the UDP client level or UDP headers or anything else. It's just the payload data and some TID and tdest values, and everything else will be taken care of by the stack. All right, so what's the status of this stack right now? Well, the initial implementation is going to target 10 gig natively with a 32-bit data path. The parser deparser logic will be fixed at 32 bits. For higher rates, we'll use multiple instances, and we'll have some striping and destriping logic. For lower rates, we'll width convert, so you won't get a huge savings on the footprint, but it will at least work. At this point, the parser and the deparser are mostly complete, and that most of the core functionality is operational. There's probably some testing that I need to do to root out some bugs, but it's excuse me, it's a pretty good start at this point. I'm currently working on the data path and the rules engine. I have sort of a mocked up, hacked together rules engine and data path built with probably more generic AXI stream components than I'm planning on using long term. So there are some limitations to the data path right now. The packet buffering, for example, is not very flexible. Long term, I'm going to do things a little bit differently. But with the setup that I have right now, I built it on a KC105 using the low latency 10 gig MAC and that closed timing. And I was able to successfully echo packets back with reconstructed headers. So I think I have an example. Well, all right. Ah, this is what it looks like. Oops, I've got to change the title here. Um, this is what the test looks like in TCP dump. You send, well, I didn't actually send a packet explicitly, but there's an ARP request that the computer sent to the board. And what the stack did is it parsed the header and realized, okay, this is an Ethernet frame with the ether type for ARP. It extracted the header, or it extracted the payload. It passed that to the user interface. The user interface then turned that back around, and then the stack computed a UDP header and attached the requested payload data and sent that back to the host. So yeah, it included the padding bytes here. I mean, you don't see them here because it hasn't been sent on the wire yet, so it's not padded to the minimum length. Those are included because they were in the original payload that the stack turned around. Because there is no length field in the ARP request. But if this was a UDP packet, then it would take that length into request or into consideration, and it wouldn't have any padding associated with it. But yeah, so it generated the Ethernet header with some faked out MAC addresses. It generated the IP and the UDP header. It computed the checksums and the length fields and everything. So it seems to be, for the most part, doing its job. Now I need to go remove some of this hacked up stuff with a proper implementation. So that's a good start. I just got that initial demo working last night. So yeah, I'll continue chipping away at that over the next couple of months here, and hopefully we'll have something usable soon. Definitely by the end of the year. At least at 10G. I don't know about the higher rates. We got to work in a 10G first, and then we'll chip away at the higher speed stuff. All right, so a little more details on some of the internal components here. The parser, it's a fixed 32-bit data width, and it supports VLAN tags, IPv4, IPv6, UDP, TCP, and it's also capable of handling, on some level, extension headers and TCP IP options. In the case of the parser, it basically just skips over them for now. Potentially, some of this stuff will have to be handled in various ways later on. How that works is TBD, but at least being able to skip over them means that you can still do something sensible with the packet as opposed to just dropping it on the floor like the old stack did. The parser also computes the whole frame checksum based on the header fields, the payload length, the L3, L4 header offsets, RSS hash, and it validates the IPv4 header checksum. So quite a bit of stuff going on in the parser. And like I said, I tested this on the KCU105 at 322 megahertz and seems to work just fine. The deparser similarly is built with a fixed 32-bit data width. This can handle VLAN tags, IPv4, IPv6, UDP, and TCP. The extension headers are currently not supported because, well, I don't know the best way to pass those around between the internal components at the moment. So I'm going to do some ruminating on that. At some point, I'll probably have like limited support for something. But exactly what at this point, I'm not entirely sure. But it does handle the IP header and the TCP UDP checksums. So it'll compute and insert the IP header checksum, and it'll compute and insert the TCP UDP checksums. You also have to provide the deparser with the checksum of the payload data. But put all the pieces together, it does the job and generates the packet as requested. And this one again has also been tested on the KC105 at 322 megahertz. And then there we go. We have the one of the one of the first packets sent through the very hacked together stack. So starting to see some signs of life, but it will be some time, I think, before you'll be able to actually implement a proper client. Big thing though is now that I have um, something working in hardware, I'm probably going to start committing a few pieces of the stack, like the parser and the deparser modules, and some of the other pieces. So I don't like committing a big complicated thing before I've done any hardware testing at all. Um, but yeah, now that we have a few pieces with some meaningful signs of life, we'll start to see a few of those bits and pieces appearing in the taxi repository. So stay tuned for more details here. I think that's all I got for today. Yeah. So if anyone has any questions or comments, go ahead and fire away. Well, I think somebody's been, I have not been seeing stuff in the chat here. I just noticed that. Okay. So a couple of questions here. So somebody asked, or Logan asked, are we testing with an external grandmaster or using the FPGA's oscillator? So for all of the testing that I've been doing with the timing stuff has been with the internal oscillator on the FPGA. I've not been using an external grandmaster. Um, Partially because I don't have any grandmaster stuff that's at well, for several reasons. One is I don't have any grandmasters at 10 gig, 25 gig. The other piece is that I need to be able to do these phase measurements on the master end. So even if I had a grandmaster box running at 10 gig or 25 gig, it wouldn't really help very much unless that grandmaster was like capable of doing these picosecond level measurements. So there might be some network test hardware that can do that, but I also don't have that. So I kind of got to build the whole thing myself. Um, but yeah, that's a good question. And I guess if I'm not using an external oscillator, we're dependent on the stability of the internal oscillator. So if that thing is drifting all over the place, then yeah, that could potentially be a problem. So far, it seems to be stable enough for what I'm doing. Obviously, that could change, especially if we're talking about going through a really long length of fiber or something. But um, yeah. Uh, let's see. What other questions have I got here? I mean, feel free to unmute and ask directly. We don't need to do this in the chat.
Sure.
Um, so Julian said, could be interesting to test some NIC++ designs like MPLS and SRv6. What is
Yeah,
SRv6?
I was. It's a protocol that look like MPLS but with IPv6 options. Um, option header rather than specific. I don't like that too much. It's like a hack bug, but it's used in big networks now.
Hmm. Okay.
And yeah, look, you can have a look at this quickly. Basically, it's like MPLS. It's reusing IPv6, address space, the 180 and
Hmm.
28 bits. And in fact, it does headers. And with that, it establishes like MPLS, a switching route.
Hmm.
And that's used inside, for example, 5G networks, inside network operators to have multiple class of service and all of that. It's a little
Yeah.
bizarre, I admit. But I've come across that we have in France a big operator that is completely left MPLS and switched completely to that. And the advantage here is that since it's reuse IPv6, you don't have any other specific switching
Oh,
switch
interesting. Yeah.
to buy actually. So
It's
yeah, it's
it's always funny the creativity of the people
yeah,
that come up with these protocols. Like, oh, hey, let's take this existing protocol and abuse it to do something completely different, just
exactly,
so
and
we
it's
can take
even
advantage of all the hardware.
yeah, and the people get completely over the board with that because, for example, one guy said, "Oh, okay, but by putting multiple option header in that, we can even create like a Turing machine and say that we can create like um, a
So it's
processor with a very
so
small
so
interface."
so okay. So it's funny you mentioned that because I was actually had this thought couple of weeks ago, or maybe longer than that, about okay, how do you actually parse like IP extension headers out of and all the other headers, like if you wanted to build like an engine that could parse this 400 gig, for example, traffic and get all the extension headers and everything else, like how the hell do you do that? And then finally I realized it's exactly the same as the front end of a superscalar CPU, where you have to extract all
Exactly.
the different instructions, where you have a variable length instruction set, right? It's exactly the same thing because you don't know how big all the extension headers are until you're in the middle of processing it. So, yeah,
Oh.
it's you basically need to build a freaking CPU, literally,
Exactly.
to decode these
They did.
things. So, from
And
my point of view, screw extension headers because they make things way more complicated. But
yeah,
yeah, then you get the
exactly.
software guys going, "Oh, hey, we control this crazy stuff with extension headers." It's like, oh,
Yeah,
what
exactly.
are you gonna do?
And yeah, and you already have some kind of hardware implementation of this protocol by Cisco and all of that, but
Right.
also you have some kind of the DPDK, for example, have implementation of that for reference. You know,
Okay.
if you need to run test or something. But I'm talking about this because I've been in my work. We have a lot of research paper people that do stuff, not my
Hmm.
case, but okay. And yes, they wanted to investigate the possibility for FPGA-based handler. Of course, you don't have to handle the everything in SRv6. You just have to handle some headers, some
Right.
specific one. Uh, I don't explain very much, but very well. But yeah, I mean, in the documentation, it's written that, for example, you can have some kind of very basic switching stuff at the very beginning of the extension header, and
Hmm.
the rest of it can be parsed later on, more in the edge to do some other stuff
Mm.
like okay.
Yeah, I mean, I guess that's kind of the idea with some of the option headers is you don't have to process all of them at every step. You
Exactly.
can
Yeah.
look for specific headers and handle it.
Exactly.
But then, but you
And the
still need to,
header they're always
but the problem is you still need to deal with that freaking, variable length header list.
yeah,
Just
I agree.
sorting through
But
that to find the header you want is it's
yeah,
not an
but
easy thing to do.
each header within the extension header list is always at the same offset from one another.
Hmm.
So you have, I don't remember the size, but at least it's always the same separation between each. So if, for example, you want to check if one header is interests you, well, it takes a little bit of logic, but you
Yeah.
can at least check one byte every X byte and verify that you have one for you or not.
Hmm. Yeah, so I think the extension headers they're fixed on like 128 byte increments or no,
Yeah,
128
exactly.
bit
Something like
increments.
I don't remember exactly, but yes,
64?
that's
I
something.
can't remember. Yeah, I'll have to take another look at that. But yeah, it's not as terrible as it could be otherwise, but it's not optimal. So
Yeah, and there
honestly,
is some refinement.
the more annoying part is that, because your IP options are in increments of 32 bits, that it shifts everything subsequent to that by random increments of 32 bits. So it's like, well, does it make sense to build something that can only look at, say, 64-bit locations versus you probably need to look at every 32 bits. But anyway, I don't know.
Yeah. So that yes, that's just an investigation for me
Yeah,
because I was wondering, and since on my own I don't have big cards for
yeah.
myself, I just have the smallest one, like the Arctic 7 or all of that. Then the ones that are easy enough to find. That's why I was quite happy that you plan to do the smallest one. You know
Oh, right. Yeah.
the
Well, I mean, the flip side is all sorts of weird stuff pops up on eBay regularly. So,
yeah.
I try to post stuff whenever I see something on eBay, especially if it's in Europe or something. I'm like, oh, well, something in Estonia. That doesn't help me because that's going to be very expensive to ship. But somebody in Europe
Yeah.
might be able to jump on that. Like, I think there was a
Yeah.
couple of ZC102s and maybe ZC106s or something
Yeah.
shipping from
I
Estonia or Finland or
unfortunately
something. It's like,
I missed one like a few weeks ago. One which was very very cheap,
Hmm.
and unfortunately you have to shoot very fast
Oh,
because you're not.
yeah, yeah. When that, I mean that's my strategy. If I see something that I really like, I just buy it. If I see something that I think somebody in the Corundum, community would like, I just immediately onto the board channel, post it as quickly as possible, in the hopes that. But the thing that's slightly annoying is that I don't think I've ever really seen too many people post, when they've nabbed one of the things that I've posted about. So that would be fun to
Mm,
see, like, because I'm like, okay, well, if nobody posted, then I guess it must be somebody else that got it. Um, but
yeah.
yeah, there was one like Alveo board or something that was like 600 or 700 bucks out of Australia, maybe.
Mm,
Yeah, I'm like, okay, this is
yeah.
this is gonna go quick. I think it did, but I don't know who got it.
Yeah. I think as well. But yes, I'm looking mostly in Europe because otherwise it's too expensive to ship.
Yeah, yeah.
So yeah.
I mean, sometimes, if the board is interesting enough, then you deal with it. But yeah,
Uh,
well, we'll see.
Especially
I'll
it's on my
definitely
own.
continue posting.
It's not on my company. It's on my own. So yeah, it's
Right,
kind of.
right. Yeah. Well, if it's in your company, they'd probably be able to get you some pretty nice boards, I would hope.
Yeah, on the company we have UltraScale Plus, the Alveo boards.
Yeah.
We have three Alveo boards already. So
Okay,
that's
okay.
okay, but I mean they are used by other people, so I cannot play with them too much.
Yeah, that's the downside with shared hardware. You got to share it with
Yeah,
other people.
yeah, exactly,
Yeah.
exactly.
All right. I think there were a couple other questions here. What have I? Well, okay. Let's see. I guess in terms of the MPLS and the SRv6 stuff, I guess it might be worth thinking about if there's any modifications that would need to be made to like the parser and deparser modules to support that sort of thing. I don't know much about
Yeah,
MPLS or SRv6. I guess if SRv6 is basically just IPv6, then maybe not much extra is needed. But if we're talking about a bunch of extension headers, then maybe we maybe we need to do something about that. So
yeah.
I'll do some ruminating on that.
Yeah.
But yeah,
I will try to also document myself a little bit more on this and see what
right.
I can do.
Yeah,
So
and the other thing too is that sifting through a big complicated standard is just to figure out sort of what would be needed to do some basic parsing of the protocol is tricky. So um, if you've got some kind of more concrete examples in mind for MPLS and or
yeah,
SRv6, that might be worth,
yeah,
a
yeah.
really
Uh,
short write-up or something just for reference.
Actually, what I find is that MPLS is being phased out on the company
Hmm.
because of course uh, with the augmentation of the data rates, people always change their hardware, they switch hardware on the data center of that.
Hmm.
And so since SR V6 seems to take the lead, now the people that in ISP, the people that are moving up there or in data centers, they are buying new stuff, and so they are moving protocol as well. It's not, and NPLS has always been a nightmare to share labels and all of that. It has been always uh,
So I guess you've got similar problems with MPLS as you do with VLANs, right? Because you've got a somewhat limited code space, and everybody's got to agree
yeah, yeah,
on
exactly.
whatever. Yeah.
Mostly it's used inside an ISP.
Right, yeah. I mean that makes
It's not
sense. If
shared.
if if you're
Not
building
supposed
the
to
whole
be.
thing internally, then yeah,
Yeah.
that would work nicely. And then I guess the idea with MPLS is that you could, tunnel MPLS traffic through an MPLS network, basically.
Yeah.
And then you're just not looking at whatever is inside of that. Um, but
Yeah.
yeah, and that
So
would
yeah.
potentially eliminate some of the problems. But yeah. Anyway, yeah, I don't know that much about the whole ISP side of things. Mostly I just know a few things about the data center side, which doesn't you I guess they are starting to use some more of that stuff in the data centers. Like I've heard of protocols like BGP being used in various data center contexts. I guess when it gets big enough, then you need
Yeah.
that because usually you think BGP is just an ISP thing, but
Yeah,
um,
exactly. But yeah, at the time, the data center side was simpler because with VLAN you had enough, and
right,
at worst you do Q and Q and you had still enough. So, but when you start to think class of service, different class of service for 5G, sharing the same low-level network between operators and all of that, it gets complex. So
yeah.
here
And
it's
data centers have been getting bigger and bigger and bigger,
yeah.
and they're doing more and more complex things internally. I mean, think of something like
Mm.
AWS, right, where you can
Yeah,
basically
yeah,
have,
exactly.
private networks between, random VMs. Like
Mm.
that's tricky.
Exactly.
Oh, is that
So yeah,
VXLAN is another. There's so many different
yeah.
so many different protocols for
VXLAN,
this.
VXLAN is more like between data center because it works over UDP.
Right.
It's basically a protocol over UDP. So
Yeah, I was thinking, how many other
but
protocols are there? There's VXLAN, there's a GRE as well as another thing that I've
uh,
seen.
yeah,
Um,
yeah, yeah.
yes.
But that's an older protocol, and especially
Right,
they are all working on IP level, over IP level, like
right.
UDP or TCP. Here we are talking about lower than IP, like in place
Gotcha.
of IP, basically. That's the thing with SRv6. It tries to mix both world a little bit, using the extension as a sideway. Well, it's well, but yeah, have a quick look if you want, and just to have a feel of how it works.
Yeah.
It's
Yeah, well, it's
a
good to
quick
know
video.
kind of what's coming down the pipe because I've heard
Yeah,
of MPLS, but SRv6 I've never heard of that before. So
mm,
definitely worth some background reading. I'll look into
yeah.
that. Maybe in a couple months.
Well, not don't. Okay. But the issue here is maybe in a couple of months they will have changed already this for another new protocol. So
Oh,
you never
well,
know.
in which case, what's the point, right?
Exactly. But yeah.
Actually, speaking of ISP type stuff, I didn't even realize you could get these, but I picked up a couple of these ZR4 transceivers that are
Mm.
good for 80 kilometers
Yeah.
unamplified, which is kind of interesting. That's
Yeah.
uh that's a pretty good link margin on these things.
Absolutely. And be careful because it gets hot very quickly.
Yeah, I noticed that.
So
I
yeah.
I definitely noticed that. Yeah, and also with transceivers like this, you might need to attenuate a little bit
Yeah,
so you don't
you
blow it
do.
out.
Yeah, if you put only 3 kilometer of fibers, you have to have a 30 dBm attenuator in front because you will just burn the
Yeah.
the stuff.
Well, I guess with these things, I think the output power is about plus 10 dBm, which is
Yeah,
well, with the
something like
specific one
this.
that I got, which is not it's not crazy. So I don't think you would damage it necessarily by even a short loop back, but it definitely you would saturate the receiver.
Yeah, if sure
So
it won't work, and I'm
yeah,
not that sure you will not burn the receiver with
yeah, it's
that
like
kind of power.
well, I mean,
Uh,
you potentially could. I think it's going to be dependent on the
Yeah.
module and the. I have
Mm.
not actually. So these are from Monara Network, so I don't actually know. I've not been able to find any documentation for these things. But
Hmm.
yeah, the first time I plugged it in, I went straight through my nice optical attenuator here to figure out what the link margin was. So I'm like, okay, I'm
Yeah,
going to set this to 20 dB, turn it on. Whoa, I got a link.
absolutely. Yeah.
Yeah, usually
Yeah.
20 dB is they're going to get nothing, but 80 kilometers at 1310. That's impressive
Yes.
because it's 80 kilometers at 1550, that's not bad. It's like zero
Yeah.
point 0.2 dB per kilometer. That's not too bad. 80 kilometers
Mm,
at 1310, that's like zero point 0.3 and change
mm,
potentially per kilometer. So that's a lot of loss. Yeah.
yeah.
Um, and then I guess for DWDM stuff, it's a whole different ball game because you can use the optical amplification and whatnot to go really far. But
Yeah. But that's again a different
whole
thing
different ball game.
altogether.
Yeah.
Yeah.
I mean, I have some of those too, but
Yeah.
the what are these things?
Well,
The
what I find impressive is that
Marvell
mm,
100 kilometer or 100 gig 80 kilometer 195.9 terahertz channel 59 Oh, right. These are branded Marvell, but I think the original company that made them is Infi.
Mm.
They're two lambda DW two lambda DWDM, so they squeeze two 50 gig subchannels into one DWDM channel. It's kind of funny. It's a and the funny thing is these do not work in loopback.
Yeah.
The output power is like minus 10 dBm, which is not
Mm.
enough. So
This
you
is not
you got
enough.
to go through
You have to
amplifiers to do
amplify.
anything
Yeah,
with them.
yeah.
Yeah.
It's yeah. But at least it doesn't hit so much.
Right. Yeah.
Yeah. The one I find impressive is that this one. It looked like a regular one, but well,
Hmm.
you cannot find it's reversed. But it's a GPON SFP,
Oh, right.
you
Yeah.
know, and there is a full micro Linux in there. So you have when you connect to it, you can find you can connect to a specific IP address, even if there is no fiber on the other side,
Oh,
and
interesting.
then you can get in and
Well,
you
I
have
guess
a
I guess
full
I guess
Linux.
it's basically like just like a whole modem, but
Yeah,
in a transceiver.
exactly. But
So yeah,
stick in the SFP itself.
yeah, yeah.
It's
Which I
and
mean
that's
it
impressive of the size.
right. I mean, to some extent, it kind of makes sense because how big is a Linux SoC these days? If you can make a pretty powerful one small enough to put in a phone, makes sense. You could squeeze one in a
Yeah,
transceiver,
but
and then you just have 10 gig.
this is even smaller than a phone, and you have to
Right.
stick the SoC, but also the NAND and also the memory
Hmm.
and the transceiver for both sides.
Right.
Uh, with some provision for UART pins that can be exited right here, or right here, near the connector itself.
Oh,
You can solder UART
that's
pins in
interesting.
them.
Yeah.
It's crazy. Yeah, yeah, it's completely, and it
Okay.
costs
That
something
that
like
is pretty
20 bucks
impressive.
now.
Yeah.
And
Okay then.
yeah, well, it's crazy. So yeah.
Sounds like it. Yeah. This is
Uh,
pretty neat little units.
Yeah,
All
and
right.
they can do this one specifically, they can do 2.5 gigabit. It's not only
To
one
the
gigabit
host or over the
to the
PON?
host, to the
Okay.
host.
Oh, okay. Interesting. Oh, that's not 10 gig, but it's also not 1 gig. It's somewhere in the middle.
Yeah, it's
Okay.
2.5, and of course on the GPON size it's two gig because the GPON is only two
Right.
GPON standard. So
Right. Okay. Yeah, I mean that's definitely convenient because you can just whack
yeah,
that into your switch and then plug the
yeah,
cable in and you're done.
exactly. You just have to do the configuration beforehand, and then up you go. So that's very useful.
Yeah. Nice. See, somebody, I think, let me see if there's any other questions here. Somebody asked if I've already started to take a look at the Xilinx 100 gig cores, 400 gig cores. No, because I do not have a Xilinx board with a 400 gig core on it. So I only look at stuff that I actually have a board for. I happen
Yeah.
to have one of the Stratix 10, or not Stratix 10, Agilex iSeries dev kits
Hmm.
around here somewhere. I'm forgetting where I put it right now. But yeah, I don't have any Xilinx boards with the 100 gig with the 400 gig transceivers on there, or the 400 gig max. I do have a couple of first generation Versal parts, the ES, um, but those I think only support up to 100 gig operation. I think that only 25 gig NRZ on the transceivers in that ballpark. The that round of that whole stack of VCK 5000s I got a while ago. Speaking of stuff that pops up on eBay, 500 bucks a board. I'm like, where's my credit card?
Yeah, I have to be more proactive on eBay, maybe.
Yeah. Well, I mean, a lot of that's just about timing. I've definitely,
Yeah.
gone on. Sometimes I go look at to see what, items sold, and I'll see something that sold like 2 days ago. I'm like, oh man,
Uh,
I didn't even see it because it went so quickly.
yeah.
Um, yeah, what are you gonna do? Um, well, I got so many of these things. I'll have to think about that. It's like I got freaking 8 of those. So do I need 8? Probably not. We'll see. But
Yeah.
yeah, so it's the first generation Versal. It's the engineering silicon parts. I don't know what kind of errata they might have, and you got to use an old version of Avado to target them in the first place. So, but it's a Versal part. and stuff can be done with that. But yeah, so I think they only have the NRZ 25G NRZ transceivers, and I think the PCI Express interface is only up to Gen 3 by 16. So it's not really a significant step above, like the Albio U200s and whatnot in terms of the interface capability. I guess the new ones, the V80s, are potentially, pretty nice cards, but at like 10 grand a pop or whatever. Might be a while before I get my hands on one of those. We'll see. Maybe it'll happen sooner depending on, what pans out with, consulting and stuff. But yeah, for the time being, I just got to deal with what I got here. So yeah, like the
Yeah.
ZRF8 board, that's through the research project. So um I didn't I don't have the funds for one of those. It's like another 10 grand for
Yeah.
that board. So yeah. What are you gonna do?
And you have to
Downside of this
for
stuff,
the
it can be quite
400
expensive.
gig. Yeah, for the 400 gig, you have to have something to test against as well.
Yeah, so I
Uh,
have a couple
uh,
of 400 gig NICs. They
oh, okay.
yeah, that's a whole nightmare in and of itself. The I have two of the Mellanox 400 gig NICs, the MCX 75310 dash neat. Yeah, the heat ones are only 200 gig. The neat ones are
Mm,
400 gig. I don't know where the hell they
okay.
came up with this naming scheme, but okay, whatever. And then these are not QSFP-DD, they are OSFP, and they are not any OSFP, they are 4 by 100 OSFP. So you got it, and they're not normal OSFP, they're short OSFP. So yeah, it was a pain in the butt to find modules that actually plug into these things. Number one, and number two, to figure out how to get from there to an FPGA. So I think I've managed to score some of the four-channel parallel single mode OSFPs. I think I have two. So I got two NICs. I got two of those, and then I have a few of the XDR4 QSFP DDs, which I think are compatible, but I have yet to bring up a
Yeah.
400 gig Mac to cross
Mac,
connect
yeah.
it and see if it actually works. So
I
yeah,
understand.
I haven't had the time to dig into that yet. So at some point, hopefully soon, I'll chip away at that and see if I can get that operational. Because yeah, I got two computers as well
Mm-hmm.
for 400 gig test stuff. So these have the this was another thing that popped up on eBay. I saw these things, 2,500 bucks a pop with the I'm forgetting what CPU they have in them now. One of the Xeon W7 workstation CPUs, but either the current generation or like one generation behind. So they've got four PCIe by 16 slots. Two are, well, the HP machines here don't do Gen 5 on everything, but they give you two slots at Gen 4 by 16 and two slots at Gen 5 by 16. So that's like a perfect setup for doing the 400 gig stuff because I could put, two cards in there. Um, and basically, you know, use NUMA, separate it, and run both the transmit and the receive on the same host. Or I can cross connect them because I got the two machines. So I actually finally got a second. I for a long time I only had one of the NICs. I finally got a second NIC, and I was able to actually try um, actually sending traffic between the two. I think I was only able to get it up to like 250 or 300 gigabits per second, something like that. I wasn't able to get up to 400, but there's probably some tuning I need to do. So, one step at a time. Those NICs also get
Sure.
very hot, and the OSFPs also get very hot. So, what are you gonna do?
Yeah. Yeah, that's complex. I agree.
Yeah.
Okay.
So, at some point, I'll be doing more stuff with 400 gig, but I kind of got to get all of the groundwork laid first, right? I got to
Yeah,
get the
sure.
core of Corundum ported over. I got to get all the taxi stuff ported over. So that's progress is being made there, right? I got all the Macs transferred over. I got AXI stream stuff. So now I got to do PCIe stuff. And then probably the next thing that I'm going to work on is actually just building the new kind of Corundum micro thing. And we'll see how that works. So I got to figure out how to make that work, both AXI and PCIe efficiently. Um, and then we'll test that
Hmm.
out. Somebody expressed some interest in that a while ago. I'll have to follow up with them and see what what the status is
Okay.
with that. But yeah, it's possible that won't, but that particular lead won't go anywhere. But what are you going to do? Um, but yeah, no, I think I've come to the conclusion that that particular one is going to be useful just from a prototyping perspective. So it's
Yeah, absolutely.
while why my original idea is that why should I build something so low end? That's just a waste of time. But the flip side, it might actually be easier to prototype something like that, get the interfaces kind of figured out, and then the higher performance stuff is the same interfaces but higher performance. So
Yeah,
yeah,
and sometimes you don't need to have big performance. You have to need, for example, for the timing. Sometimes you have to have a very precise timing, but not having a packet that exit very often.
right, yeah,
You know,
yeah. It gives you some more trade space to play with.
yeah,
So yeah,
yeah,
and I figured this could be something that would pair nicely with the Zircon stack as well. So for example, if you wanted to
exactly.
build like a middle box, maybe you need to, Zircon stack for, 100 gig to your, hard application, but maybe you have a little soft management core that only needs a few packets per
Yeah,
second. You don't need a massive
yeah,
stack for that. So
yeah. And for all the debugging stuff, it's easier to have maybe a slower rate. You can analyze easily with you know, just
yeah, you can probe
Sononic.
more stuff with the
Yeah, you
with the
can for
ILA
more
and actually
stuff.
see
Yeah,
everything. Yeah.
yeah. So you can
Yeah.
do all the setup and testing and all that low speed, and then just once your stack is good, you can put it on a better card or
Yeah. Yeah, it makes a
try
lot
to
of
add.
sense.
Hmm. So
Yeah, I mean that's
and
how I build a lot of the like AXI stream modules as well, right? Like for the
mm,
concatenator and the slicer, for example, you build it for
yeah,
1 byte first. You
yeah,
make that
exactly.
work, and then you go, okay, well, what the hell do I need to do to process 8 bytes per cycle?
Exactly. And also it opens the number of cards that you can find, maybe also to work
Right.
for other people to work on it as well.
Yeah. For example, I
So,
recently got some of these,
okay. Oh, okay.
which are the
Lattice. All
lattice
right.
parts, right? And they've got
Mm.
one
Yeah,
lane of PCIe and a couple of 1 gig ports. So
exactly.
now, obviously, then I got to
Mm.
get the PCIe stuff working on lattice, so that could be a pain, but
Yeah,
that's certainly a
I
much lower
agree.
cost part.
So yeah, and I also have a lot of no, not a lot, but a few Arctic 7
Hmm.
cards that you can find now for very low cost,
Right.
and so maybe it's easier to survive because
Well,
finding an Alveo card it's
so actually, I was going to say,
already quite
speaking
challenging.
speaking of random stuff off of eBay, there's a couple of very interesting cards out of China right now. One of them is this Alibaba card with a KU3P FPGA on there. I think it's what
Mm,
8 lanes of PCIe and two SFP 28s probably, and it's like $200 plus shipping. It'll take like a month to
mm,
show up or whatever, but that looks very interesting, and I'm hoping to pick up a couple of those. And then, so there seems to be just one listing for that, and they're ex Alibaba cards.
okay.
So there's probably going to be more popping up at some point. Who knows, really? There's also a bunch of boards with the KU5P that it seems like somebody is making these. I don't know where the FPGAs are coming from or whatever. They seem to be maybe
Mm,
more in the $300 range. They look more like dev boards, right? They have like I think a
yeah,
QSFP and an SFP on there, and there might even be like an FMC connector and some other stuff. They look like pretty interesting boards. Um, they're a little bit more expensive than the KU3Ps. Um, KU5P technically requires the Vivado license, but
yeah.
there's potentially a couple of
Mm,
ways you could use those. One of them is that you can procure a Vivado license. The other thing
mm,
that we've discovered is that you can change the device ID on the in the bit file. So what you can do
okay.
is target the board as if it was a KU3P, and then use
Mm,
a script to change it to KU5P, and then you can load it. Because
okay.
KU3P and KU5P, it's the same die. The limitation
Uh,
is Vivado software.
okay. Yeah. Okay.
Procure license opens GitHub
I'm
finds
no.
license lol. Yeah. Yeah. I like the word
Okay.
procure.
Okay. The
Anyway, so
KU5P, yeah, is
so
that's
the other thing I was
interesting.
going to say is that you can actually go the other way, and you can target the
Mm.
KU3P as if it was a KU5P, if you have a
Mm.
Bravado license, and potentially that will also work. Obviously, the package has to be the
Okay,
same, right? If the package is
of
different,
course not.
that doesn't work. I don't think that's a problem for KU3P and KU5P. Uh, I think Arctic's Ultrascale, some of them are also KU5P. So if you have, I can't remember which one. You look at the config user guide. You
Mm.
look at the bitstream size, and devices that have the exact
Okay.
same bitstream size have the exact same die. Uh,
Ah, okay.
so yeah, that's generally how that works. So you just got to get the same package because a lot of these parts they tend to be actually so it's a better deal than it actually initially sounds, right? If you get a KU3P, it's like, oh, Vivado is software limiting the number of LUTs that you can use below the
Mm-hmm.
maximum. But here's the thing, it doesn't lock out specific LUTs. It just limits the total number that you can use. But you can use
Okay.
all the LUTs, right? So
Yeah.
that means that 90% of a KU3P is going to be really easy to hit versus 90% of a KU5P, right? You're going to run into
Yeah.
less routing congestion and such. So buying a
Yeah. That,
KU3P, you're basically buying a KU5P in terms of, the size of the die. So, um, yeah,
yeah. I think I
it's kind
just
of
find
interesting
the
to think
card
about.
in for me the KU5P, the card you were just
Yeah,
saying, it has one QSFP28. That's it.
I thought I
I
had one
think it.
QSFP and one SFP maybe,
Uh, I
but
found
maybe
that
maybe I'm
one with
mistaken about
yeah.
that. Let me double
I
check.
found
It's
one
been
with
a
a
while
one
since I.
QSFP, but it also have other ports like
Yeah,
debug and also
maybe I'm getting
FMC port.
something. Oh, okay.
Mm.
Yeah, no, never mind. It doesn't have an SFP. It has, I think, an RJ45.
Mm.
Yeah,
Okay.
and these are in
I,
the
I found
300.
one that is a PCI card which is about 500 euros. So yeah, that would be acceptable. I have to check.
This is the board that
Yeah,
I had in mind. Yeah, these guys. So
yeah, it looked like what I found also.
yeah, yeah. So it
It's a
looks
bit
like
more expensive.
there's a gigabit Ethernet, there's SD
Mm.
card, there's a USB-C
Yeah,
debug port, FMC port, big 40 pin header, I guess, for IO,
yeah,
QSFP
YO,
28. Okay, so it
always
says
useful.
PCIe 3.0 by 4.
Yeah,
By
it's not
4?
very fast, and no,
Why would they be
no,
limited to by 4?
yeah, maybe because they lack
This this
lanes
this
and they
is this
wanted.
is well, yeah, yeah. There's probably not that many transceivers on these, but it's like this is one of the things that kind of annoys me about some of these.
Cards. Yeah, they
Yeah,
limit the size of the PCI bus.
yeah. It's like why do you limit it like that? It's like, come
Mm,
on, guys. So the stupid thing is it's
mm,
a by 8 connector. So I saw the
yeah,
connector and I'm like, oh, it's by 8.
yeah, and
No, it
no,
isn't.
it's not. No, I agree.
Ah,
But on the other hand, to do just development, it's not a big issue. You know, if you're not wanting performance with that, it's just a development board basically.
right. Yeah. Yeah, no, I mean they look like good boards. You can
Mm,
certainly get a lot of mileage out of those things. I mean, with the Gen 3 by 4, you can't do 100 gig, but you could certainly
mm,
do 10 gig and 25 gig.
yeah.
I think you do 25 gig. So it's 8 gigabits per second per lane. So
Mm,
so 4 lanes is 32. So yeah, you could do 25 gig on one lane. Um, and that would work. I think these have 25 gig capable transceivers. I guess there's then the question of do you have the signal integrity on the board for 25 gig?
mm.
Um, Not sure about that, and also not sure about their clocking infrastructure and whatnot. Oh, somebody asked, do you foresee Corundum variants being cross-compatible, one light to multiple micros? Um, well, I guess what do you mean by cross-compatible? My plan is that they're all going to use the same driver.
Yeah.
So in that sense, it would be easy to switch from one to another. But I'm not sure if you have a particular sense in mind here. I mean, feel free to unmute and just ask directly. That's fine.
Okay, 5.
Hey, sorry, I'm happy to unmute.
Might be a little bit more efficient to do that than to pop stuff in the chat, but yeah, whatever
Yeah,
works.
probably. I was talking more for developing like a multi-point type of topology using one light on the host end and then trying to connect that with multiple of the micro devices.
Um, I mean, I don't wait, so you have one light instance on the host end. Oh, and then multiple
Multiple
micros
micro
on
instances.
the. I mean, yeah, I guess you could do that. I mean, so the idea is that all of these are just, they're NICs, right? So you're just talking about exchanging Ethernet traffic between the host and the network. So, you
Yeah.
put a network switch in between and you can communicate between whatever variant you want, as assuming you have either you put compatible Macs on them or you have a switch that can do the necessary, conversion. Like, for example, maybe you need a switch with a bunch of 1 gig ports and a couple of, SFP pluses at 10 gig, then you could make that connection, right? So,
Mhm.
um,
Yeah, I was thinking more on the like optical end of it. If you thought they would be optically compatible, if you're doing an optically switched.
um, well, so with I guess the question is, why would you want to use the micro one at all for optical stuff like that? Well, so it seems like you have some sort of a topology in mind, right? So,
Well,
um,
a little bit. I
a
mean,
little bit, okay.
mostly for the micros, did you not assume that they would be having a transceiver on there?
Well, so the micro, the way I envision it is it's more just a little block that you can drop into a design and then connect to whatever transceiver you want. But most likely, it's going to be limited to a couple of gigabits per second of operation. So you
Mhm.
could hook it up to a 1 gig transceiver, which could be optical, could be electrical. I mean, from the Corundum standpoint, it doesn't matter.
Agnostic.
Um, but if you wanted to put on a 10G transceiver, you're probably better off using just a light version in the first place,
Mhm.
which will have because the whole point with the micro version is that we're trying to get the footprint as small as possible. So all of the control path is going to be optimized for size, right? We're going to
Okay.
get it as small as possible. We're going to make it as simple as possible. The trade-off is that it's going to take a lot of clock cycles to do anything. And at 1 gig, that's fine because minimum size frame, 64 bytes,
You've
64
got time.
cycles. Yeah. Um, for light, the idea is okay, well, let's try to target an aggregate bandwidth in the 10 to 100 gigabit per second range, which means maybe 1 packet per cycle, something like that. So you
Mhm.
need much wider internal interfaces and whatnot to handle that. So it takes up a bigger footprint on the FPGA. Doesn't make sense to run something like that at 1 gig, but it doesn't make sense to run the micro version at 10 gig, right? So
Mhm. Yeah.
different size designs for different data rates. So if you're interested in running it, say 10 gig, which if you're doing something optically, if this is for data center applications or whatever, 10 gig I think is kind of like the bare minimum rate that you would want to run at.
Mhm.
Then we're probably talking about, at least the light and maybe NG depending on what you're doing, right? So, um, but I mean, there really should be no compatibility issues per se because the the whole point is that again we're just exchanging traffic with the host. How you get it off of the card is
Mhm.
a different discussion, basically. Especially if you're
Yeah.
trying to do something non-standard where you have maybe some weird optical transceivers or optical switches or something. Um, Corundum is just how you can get the data over to that system. Oh, the other thing too is that light is going to be really stripped down, so it's not going to support multiple queues per port. It's not going to support transmit scheduling. You know, things of that
Okay.
nature is just not going to be there. Again, size reasons, right? And at 1 gigabit per second, you don't need multiple queues. You don't need transmit scheduling, that sort of thing.
Mhm.
Um, for light, then you would have some of those capabilities. Um, although that does raise the question, what if somebody wanted to do like um, TSN or something at 1 gig, right? Where you do need some of those capabilities. I need to think about that. I'm not sure the best way to handle that. Maybe there could
Fair.
be some optional thing. Um, Maybe we can have like a couple different versions of the micro design or something. because my initial thought about micro was that like you're building like a RISC-V SoC on an FPGA and you want to give
Mhm.
it a 1 gig port or maybe even a 100 megabit port or something like that, right? There's a little block we can just drop in there, connect it to the RISC-V, connect it to the port, really small, and give you good performance, right? That's kind of the use case that I had in mind. But it's a good question. There might be some slightly less trivial use cases where having something like that could make a lot of sense. Because at least historically, Corundum has been like 10 gig and up. That's what we're targeting for 1 gig. I mean, you can use it, but
Mm.
it's gonna be really bulky in terms of the FPGA resource utilization.
Mhm.
But yeah, if you want to do something like TSN where you need the not just timestamping, but multiple queues and um, scheduling,
Yeah.
I'll think about that actually, because with a lot of cycles, it might actually not be that hard. Maybe it would uh maybe that can be an option to turn that on and off. Right. So you
Yeah.
turn it off and then it's just the single queue thing, you turn it on, then you get multiple. And again, if the internal interfaces of these are standardized, then depending on how you configure that, right? The driver talks to the design and be like, okay, how many queues do you support per interface? One? Okay, great. Oh,
Mhm.
256? Okay, great. It'll figure it out. So
Yeah.
yeah, just change the parameter and then it'll figure it out. So that might be worth thinking about.
Yeah. But there is definitively a use case for TSN at slow rates.
Yeah.
Like EtherCAT is an idea. I know in satellites we use some very precise link, but slow speed as well for control. Yeah, when
SpaceWire?
you space wire?
Is
No,
that the
no,
only one? Oh, I know that's one that's used for that sort of thing,
yeah,
but I guess
but
there's also other protocols as well.
yeah, but the tendency in space is to replace space wire by Ethernet. So
Okay.
yeah, but
You,
you
you
have
you you would think they'd be using more space wire in space, but
no,
it's right
no,
there in the
no,
name.
because no, you have all this new space stuff. So basically, you
Hmm.
throw at the space as much thing as you can, and so those things have to be cost effective.
Yeah.
And
So
so,
it makes
of
more
course,
sense to use like standard off-the-shelf Ethernet
exactly,
than to use
exactly,
something custom. I mean, I guess if
and
you're on an FPGA, then in some sense you can do whatever you want, but I guess it does depend on the availability of PHYs and connectors and that sort of thing. So, um,
yeah.
if it's like if
For
SpaceWire
example,
requires some specialized components, then that could be a problem.
exactly, and
Or I
also
guess it
this,
also depends
this,
on like if you can use like an off-the-shelf Ethernet switch versus a custom SpaceWire switch, that would be an
yeah,
important
exactly,
consideration as well. So yeah, no, that's
because yeah,
it's a really really good point about asking about that. Yeah, I'll have to think about
yeah,
that. For
yeah.
there might be some good use cases for 1 gig at
Yeah. For example,
for
we have
fancier features at 1 gig.
on the platform I'm working with for now, we have only a 1 gig link to the what they call the platform, which is basically the thrusters and the control of the solar panel for power supply and reporting and all that. We don't need 10 gigs on this.
Yeah.
So it just control but you have to be precise because when you want to start a thruster at a precise moment to change orbit, you don't want to have it's just a byte to
Yeah.
send, but you have to send it at the right moment. I mean,
Oh, so okay, so you're not
mm,
doing some sort of time synchronization. It's just like you fire it off when you start it, and you fire it off
yeah,
when you stop it, that sort of thing. Is that
exactly.
literally how it works? You start, stop. It's not like
Yeah.
burn time.
See, it depends.
Oh, okay. I was thinking burn time would probably be better because if you
Yeah,
get the start but not the stop, then you could be in trouble.
no, but yeah, so sometimes more like a closed loop. Like, if, for example, if you're approaching another satellite,
Right,
you want to stop, to burn at a slow rate for unknown amount of time.
right,
And when you are closing in, you reverse the thrust in a way to slow down,
right,
or you fire another thruster actually.
right,
Okay, and that's the kind of thing they do.
right.
Mm. And all of this is linked with camera and sensors, proximity sensors, and all of that. So you have to be very reactive actually.
Hmm. So the latency is definitely important for that. I mean, maybe not
Yeah.
nanosecond level, but definitely.
Uh, the more the better.
The more the better. Okay. All right. Fair enough. Fair enough.
So yeah, there are ways.
Yeah. All right. Well, I'll definitely have to put some cycles into that then. I think probably. I mean, maybe we even bifurcate Corundum Micro into a couple different variants. I don't know. I'll have to think about that. Yeah, but
Yeah.
at 1 gig having some potential for fancier capabilities. Okay, yeah, I
Mm.
guess I can see the use case for that.
Typically in space, we use a lot of course, we use Xilinx, but I know they use also polar fire stuff
Okay,
because they happen to be very resistant to radiations. I don't know
okay,
why
gotcha.
exactly, but yeah, in vacuum, and so
Made on
they're
made on an older process technology, maybe.
maybe
No,
or
actually,
maybe.
actually they use flash and not the SRAMs. So the flash
Ah,
are
so,
more
so, so the FPGA is
reliable.
actually flashed as opposed
So,
to
yeah,
having
Mm,
to load from an external flash. I see.
it's the same as CERN. We are using polar fire for front-end
okay,
electronics as well.
Okay.
okay, okay,
And I
okay.
guess that also means it's up as soon as you turn on the power, or very quickly, because you don't need to load that, um, which takes some time. I know with Xilinx
Yeah,
devices that's potentially a problem with PCIe, because there's a between
yeah,
when you apply
exactly.
power and when the link has to work, there's a certain amount of time you're allowed, and
Mm.
that can be a problem sometimes with the bigger FPGAs and PCIe. Um,
Yeah, I found that for the for the PCI on the Raspberry Pi, for example, when they
mhm,
enumerate at the very beginning to check if they can uh, if you can find a NVMe drive, to boot on.
mhm.
And if your FPGA is not ready at this moment, then it's not ready for the rest of the session.
Yeah.
So
Yeah, so
yeah,
it would be nice if they had some options
yeah,
in the firmware on a lot of these things to say just
mm,
wait for like 5 seconds. Like I don't care how long it takes to boot. But
yeah, exactly. But no,
so
they don't.
I
So
actually had a problem with a laptop a while ago that I put a SATA SSD in it. And
mm,
initially when I installed the SSD, it worked perfectly. But then once I installed the operating system, it stopped detecting the
mm.
SSD. I'm like, what the hell is going on? Um, I don't know exact. I ended up exchanging it for I probably a Samsung SSD from different manufacturer, different controller. But I
Okay.
assumed that it took like a different amount of time to boot
Yeah,
up, and then the system didn't detect it, and
yeah, I
then
won't be
was like,
surprised.
eh? No system disk. Like
Mm.
it's
Yeah,
right there. It worked 5 minutes ago. Ah,
I agree.
so yeah, I guess PCIe has similar issues.
Hmm. Okay.
Well, it's
Yeah.
almost been going for 2 hours here. Nothing wrong with that. Anyone else have any questions or comments?
The KU5P is actually a Kintext one, Ultra Scale Plus, but Kintext, right? It's just a matter of
Yeah.
size.
Yeah.
Okay.
Yeah, KU3P versus KU5P, like I said, same die, Kintex UltraScale Plus, but the
Hmm.
KU3P is software limited in terms of some of the resources. I think I want to say they lock out the
Okay.
CMAC and there's limits on the number of LUTs
Hmm.
and
That's what I
flip-flops.
see.
But you can look at the product tables. Yeah, it's
Yeah, that's
the
where I'm at.
transceivers are the same. The packages I think are all the
Uh,
same. Anyway, looks
Okay,
like
okay.
Joe Tony needs to go, so see you later.
Okay,
I
bye-bye.
don't know if
I think I will go too because it's late.
yeah.
I'm going to.
Yeah, in Europe,
Yeah.
I understand that completely. So I got the opposite problem here. Usually people want to meet like super early in the morning. I'm like, ah.
I understand.
Ah, well, what are you gonna do? Frickin' time zones.
I
Ah,
know.
we're always
Okay.
joking. So the research project that I'm involved in involves people from NIST that do timing stuff. We're always joking
Oh yeah.
about time zones and stuff.
Hmm.
It's
Oh.
like, oh yeah, we got
Actually,
to do everything in terms of TAI. That would make things easier. Now, not even UTC. You do better than that.
yeah. I used to
Anyway,
work at NIST for years, about
oh, nice.
20. about 2000, a year 2000, when I was still young. And yeah, I spent three years there.
Doing what kind of stuff?
Oh, I was doing already network stuff, but it was higher level. It was like network, meshing and stuff like this. Public research.
So was this infrastructure stuff or research stuff, or I know NIST does a
Yeah,
lot of stuff, so.
Yeah, it was like creating it looks a bit silly now because it has advanced so much, but it was a very a kind of protocol to to do some kind of mesh network, the mesh routing,
Okay.
all of that. Of course, at the time it was very new. Nowadays you have at least 5 or 6 RFCs that treat of that.
Well,
So
you got to develop the first one, and then
yeah,
everybody's like,
exactly.
"Oh, that's a good idea. I'm going to copy that and make it
Exactly.
better or make it
Yeah.
weird." Okay,
Yeah.
so this was just kind of research into mesh networking.
Yeah, exactly.
Was this for a particular NIST project, or was this just a networking research generally?
I don't know. It was something called the Smart Lab at the time, and it was just a group that was doing a lot of research like this
Okay.
on the network, also on the beamforming.
Oh, okay. So RF beamforming.
Yeah, exactly. It was that kind of thing, but I was more on the network part, and I didn't understood a lot of things on the RF part, so already
Right.
at the
Okay.
time.
Yeah, that's pretty cool. Yeah, I was just asking because, you think of like CERN, for example, where they're all
Yeah.
about the high energy physics stuff, but they do a whole
Yeah.
bunch of engineering to support that, right? Like the White Rabbit
Mm.
stuff, which is, kind of
Exactly.
networking, that was
Hmm.
developed to support the physics, right? They got to
The
do that
physics. Yeah.
to build the accelerator and the detectors, which support the
Mm.
physics. So it's a few layers down. So, it's like with NIST. I mean, I was just trying to figure out, okay, was this part of some bigger project, some bigger measurement thing or something? But
Mm. Not
okay,
at
it's more just
for
direct
me.
networking
Yeah,
research.
for
So
me it was not that complex at the time. I was
okay,
just a small researcher at the time.
yeah, well, that sounds pretty cool.
Okay.
Anyway, there's quite a few people hung on for a whole 2 hours. That's I guess we have interesting stuff to talk about.
Very interesting
Sure.
meeting.
Yeah. All right. Well, Carlos, good luck with
Okay.
your dissertation stuff.
Thanks a
Hopefully
lot.
your slides come together nicely.
Thank you, thank you. And good luck with your work also. You have too much stuff to
Well, beats the alternative, right?
do.
Sure.
All right. Well, see you guys later,
Okay.
and hopefully you'll tune in next time around.
Yep. Sure.
Okay, see you.
See you. Bye.
All right. Talk to you.
Bye.